Now I'm going to tell you about the specific seismic waves. The first type of seismic waves we call the body waves. The body waves are those seismic waves that transmit through the earth. In other words, there's an earthquake along a fault line, and from the focus, these waves are going to transmit through the earth, in other words, through the body of the earth, and go all the way to the other side of the planet. There are two types of body waves. The first one is called the P wave, or the primary wave. The P wave, or primary wave, has the following characteristics. They travel the fastest. They are detected first at the seismic station. A seismic station is just a place that has a seismogram. They transmit through all types of materials. By this I mean rock materials of various forms, very hot, cool, solid, liquidy. They speed up and slow down as they go through materials of different densities. And they are refracted as they move through different types of materials. Refract means bend. Reflect is what happens with your image in a mirror. It bounces straight back. Refracting is bending. The second type of body wave is known as the S wave, or secondary wave. Here's the characteristics for the S wave. They move slower than the P waves and are detected second at the seismic station, hence the name. They do not transmit through liquids. Of course, I'm not talking about water. This is hot, molten rock. They don't transmit through hot, molten rock. There is an increasing time interval between the arrival of the P wave and the S wave at the seismic station as distance is increased from the epicenter. Kind of what that means is this. If you and your friend are both at Santa Ana College in separate cars, and you're both going to drive to Las Vegas, 250 miles away, and you leave at exactly the same moment from Santa Ana College, because your car can average 50 miles an hour and your friend's car can average 75 miles an hour, after 1 hour, although you left at exactly the same moment, you are 50 miles along the road, your friend is 75 miles along the road, and your friend is now 25 miles in front of you. After 2 hours, you are 100 miles along the road, your friend is 150 miles along the road, and your friend is now 50 miles in front of you. So there's an increasing interval between you because you're traveling at different speeds, and so on. These waves operate in a similar way. The P wave and the S wave, because they travel at different speeds, are not going to arrive at the seismic station at the same moment. And as you increase distance from the epicenter, from the origination of the earthquake, there's going to be an increasing time interval between the arrival of the P wave and the S wave at the seismic station. The body waves are not the types of waves that do damage generally to structures, for example. The first wave you feel, like if you're lying in your bed and an earthquake happens and you feel that little boom, 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 that's the P wave, okay? That's it right there. And remember, when that happens, what do? You lay there and you go, well, do I need to get up or not? I don't know. Do I need to get up? You're waiting for something else. You're waiting for the other waves to arrive. The S wave, if you can feel it, is going to follow the P wave very closely, because let's face it, if you can feel the earthquake, you're probably pretty close to the epicenter. You're not thousands of miles away. And the S wave would be felt as a slight amplification in all likelihood. Let's look. So here's a seismograph, and you can see over here the arrival of the P wave and the S wave. I have them circled. You can see the P wave arrives first, and then that's going to be followed by the S wave. And you can tell that these two things are separated from each other. The other type of seismic waves are called the surface waves. These are the things that are going to cause the damage. The surface waves are going to knock the buildings over. This is what you're waiting for when the earthquake happens. And there are two types of surface waves. First, the L wave, which stands for love or longitudinal wave. They move horizontally outwards from the epicenter. In other words, back and forth. And they give the kind of rattling effect to an earthquake. Then there's the R wave, or Rayleigh wave, which is named after a very famous person. They move vertically outwards from the epicenter. In other words, up and down. And they give the rolling effect to an earthquake. So the intensity of earthquakes in the past was just something that was very subjective. And then in 1935, a man named Charles Richter presented what he called the Richter scale, named after him. And the Richter scale was an attempt to basically have everybody speak the same language when they were talking about earthquakes. And so what he was doing was quantifying magnitude, which is the size of an energy released by an earthquake. Of course, 1935 is a long time ago. You probably don't drive around in a 1935 car. So as science has progressed, what's happened is we now use something called the moment magnitude scale, which is just an updated version of the Richter scale. The numbers work the same way, but it's an updated version because it gives greater concentration and a greater look to and greater focus on things like how much space along the fault plane moved during the earthquake, what kind of material was the earthquake happening in, and is the fault in? How long of an area or space or how many feet did the fault line move when the earthquake occurred? This is how the scale works. Every whole number increase results in a 10 times increase in the size and power of the waves. Now, there's actually two things going on here. We're doing the easier of the two things. For example, a 4.0 is 10 times bigger than a 3.0. This is the reason it goes up 3.1, 3.2, 3.3, and so on. 10 times bigger. So one whole number increase is a multiplication of 10 in terms of how big the earthquake is. And a 5.0 is 100 times bigger than the 3.0 because it's 10 times 10. It's not 10 times 2, it's 10 times 10. Each whole number is times 10. The 6.0 is 10 times 10 times 10, which is 1,000 times bigger than a 3.0. And an 8.0 is 100,000 times bigger than a 3.0. When the San Andreas goes in Southern California, it's likely to generate an 8.3 to 8.5 and go for up to 5 minutes. So this is going to be quite a lot of rocking and rolling. And a 9.0 is 1,000,000 times bigger than a 3.0. The 1964 Alaska earthquake generated shock waves that were 9.2 to 9.4, and the earthquake in 2011 in Japan had waves that were 9.0 and above.